Yeah, first talk. I think that technically, Patrick, you said keynote? This was the keynote? Yeah? I think that's what you said. Yeah, we'll go ahead and get started here. My name is Jaron, presenting here with my coworker and friend, Ferdous Saljooki, also known as Sal. We both work at Jamf Threat Labs, for Jamf Protect, where we develop new detections to try and keep users safe on macOS. So today we're going to talk about quite a few things, actually. We're going to talk about Gatekeeper in general. Both CVEs we'll be discussing today are Gatekeeper bypasses. So we'll get into the vulnerability discovery and kind of our process, and then we'll kind of wrap up with some of the detections and some quick notes about detections and how we pick up on this type of stuff. So first, for everybody, if you're not familiar with Gatekeeper, Gatekeeper is just a security feature built into macOS that ensures only trusted software runs on the system by verifying notarization and code signing information. So in order to run software without a hitch on Mac these days, it has to be scanned and approved by Apple. This is the notarization side of things. It also has to be signed with a legitimate developer certificate, which costs about $100 from Apple. If Apple determines your developer certificate has been used to sign malware, they can revoke your certificate, effectively blocking anything you've written. Naturally, attackers have found value in evading these types of security checks. So the first issue we'll cover today has affected multiple different archiving functionalities in macOS, and it's an issue deep within the system when it comes to parsing the bill of materials. And today we're essentially going to show how this issue doesn't necessarily seem like it might be connected to Gatekeeper, but ultimately can be abused to allow applications to slip past it. So the Gatekeeper check depends on a very specific file attribute existing on programs. So when you download an app from the internet, so long as you're using Apple APIs to do so, that file is tagged with an extended attribute called com.apple.quarantine. So when the app is opened, the operating system looks for that extended attribute. If it exists on the application bundle, then the application will be scanned by Gatekeeper. So this brings us to itch.io, a website where indie games can be downloaded and managed by indie game developers. We noticed that when we downloaded some games from the website, the application directory itself would not have the quarantine attribute on it. So most times, the other files in the app did, so you can see everything recursively here does have the quarantine attribute, but the app itself, the app bundle itself, the directory itself would not actually have it. And as it turns out, this is all Gatekeeper actually cares about when launching an application. So if we went into it, when we took these apps and we took a closer look, some of them we noticed were completely unsigned and completely unnotarized. And again, down at the bottom, you can see the path to the binary does have the quarantine attribute, but the app bundle itself did not, and completely unsigned. So we didn't believe that these apps that we were downloading were bypassing Gatekeeper intentionally by any means. We dug into it, and as it turns out, this website has its own open source tool called Butler that helps developers manage updates and get those updates out to users. It does this by taking games, which were applications in the case of macOS, and doing some manual creation of zip files with some Go code, where an archive file hosting the game ultimately makes its way to the website or to the client application that users can also use for the website. So a funny thing we noticed is that if we downloaded these zipped applications using Chrome or Firefox, there wouldn't be any issues. The user would open the zip file, which held the application, and then the application would be blocked by Gatekeeper due to its lack of signing. So that told us that the issue had to be within Safari itself somewhere, so we started trying to pinpoint where this bug existed in Safari. So one thing we did know is that when you use Safari to download a zip file that holds an application within it, that zip file appears in your dock for a very brief moment and then almost immediately is unzipped for you. By default, Safari will open what it deems safe files after downloading. Since an app is just a directory, you can really only download single files from the internet. This feature somewhat simulates downloading an application by just kind of unzipping the archive for you as soon as you've downloaded it. So if we quickly kind of rewind and watch all of that in slow motion using endpoint security, what we would actually see is that after the download occurs through Safari, the Safari sandbox is actually what's responsible for creating a temporary directory and then handling the unzipping of that archive into the temporary directory. So the Safari sandbox then takes the quarantine extended attribute and applies it to the newly unzipped application. So finally, the application is then renamed from the temp directory to whatever downloads directory the user has in their preferences. So that's everything that happened behind the scenes when you download a zip file and you have the unzip safe file features enabled. Now, obviously, that application of the quarantine attribute is a very important part of this process, because if that doesn't happen, then the gatekeeper check never actually occurs. As you can see here, this is the endpoint security rename event, where the sandbox broker is moving the application from the temporary directory to the downloads directory. So upon unarchiving the application from a normal zip file, so let's say we're not using a zip file that's been set to bypass in any way, you take the bill of materials. A bill of materials is kind of a list of software that should be installed. Generally, you think of it associated with a PKG or something like that, but the operating system does keep track of bill of materials for zip files as well. So the bomb seen on the right here will keep track of each file that gets unarchived from the zip. The unarchiving logic then goes through each file and it goes through each file in the bomb and applies the quarantine attribute fittingly using this copy quarantine function. So everything in the bomb gets the copy quarantine function run accordingly. But one big thing we noticed when analyzing a normal application in a hex editor is that the first zip file header starts at the root application directory, as you might expect, test.app in this case. So the quarantine attribute would always be applied as expected in this case. In other words, Gatekeeper would always show up, everything would work as it should. The zip files we were downloading from the internet, from itch.io, that were unknowingly bypassing Gatekeeper were actually missing this root level header and instead started at the application's contents directory. So if we take one of these, normal zip files that we had created the standard way and we remove the top level header, we see that when the bomb gets parsed, once again on the right, the application root directory would be missing from the bomb. However, the application would continue to unzip and operate normally. So when the copy quarantine function references the bill of materials and applies the quarantine attribute, it ends up missing the app directory itself, since the bomb was in some manner out of sync. So Sal and I started talking about how to take this vulnerability and weaponize it. And I quickly built a working approach where we basically take any unsigned application and compress it into a zip file. And next, we would use Python and inspect the contents of that zip file and remove all the bytes inside the first zip file header, thus making the second zip file header the new first one. And Sal said that's a great idea, or we could just run the zip command. And sure enough, this actually results in the exact same setup. that we want, where the whole app is still intact, but the first zip file header starts at the contents directory. So by building an application and running this single zip command, we would bypass Gatekeeper when downloading, specifically via Safari in this case. And again, this is because the bill of materials would end up being out of sync with the actual contents inside the zip file, and this would cause Safari to skip applying the quarantine attribute to the application bundle itself. So I'll pass it off to Sal now, who will talk about another vulnerability he discovered shortly after that looks very similar to this one, but ends up existing for very different reasons.
Awesome. Thank you, Jaron. I'm excited to share a new vulnerability that we discovered recently, allowing us to bypass Gatekeeper via the archive utility application on macOS. We reported our findings to Apple, and they credited us with this new CVE. When downloading a specially crafted archive and when extracting it with archive utility, we were able to bypass all of Gatekeeper's checks, and this resulted in an un-notarized and unsigned application being executed with no security prompts displayed to the user whatsoever. So pretty interesting. So let's compare the two CVEs at a high level. Jaron explained how we can use the zip command to craft an archive that will allow us to bypass Gatekeeper when downloaded via Safari with the auto unzip feature enabled. Using the AA utility in a similar command syntax, we can craft an Apple archive that will allow us to also bypass Gatekeeper when downloaded from the internet and extracted with archive utility instead. Although these commands look somewhat similar, the new vulnerability is completely unrelated to the Safari one, and the Safari vulnerability affected the bomb where a crafted archive was downloaded and auto-extracted with the open save files feature enabled. This new vulnerability affects archive utility with the way it applies the quarantine attribute. So let's explore this new vulnerability and how it affects Gatekeeper. So archive utility, as you already know, this is an application built into macOS located under the System Library Core Services Applications folder. It has a very minimal user interface, and users can simply create archives as well as extract archives as needed. Archive utility supports a number of archive formats. In our research and testing, we've focused on the Apple archive denoted by the AAR file extension. It's important to note the vulnerability is not specific to the Apple archive format. In the exploit section of our talk, we'll actually explain how we can craft a zip archive to bypass Gatekeeper checks as well. But for now, we'll focus on the Apple archive. When downloading an Apple archive from the internet, users can simply double-click on the archive to extract its contents. As we see here, the Apple archive is a recognized file in Finder, and the default application for handling Apple archives is archive utility. Taking a quick look at some of the default preferences in archive utility, we see that by default, archive utility will extract the archive into the same directory as the archive into the same directory as the archive itself. This is typically the user's downloads folder. So Apple has a proprietary archive format referred to as Apple Archive. It allows for multi-threaded lossless compression of directories, files, and data, including file attributes. So using the AA command line utility built into macOS, we can create and extract archives as needed. However, for our purpose, we will use the AA utility to craft various archives, and we'll explore how archive utility will handle the unarchiving. As mentioned earlier, the vulnerability is not specific to Apple Archive, and we just chose this archive format to ensure that archive utility will extract it instead of Safari with the open save files. Taking a look at the following directory structure, we have a folder named images, which contains a folder named photos, and within that we have 3 images. So a pretty simple directory structure. The vulnerability has nothing to do with these images or PNG files, and we just chose this file type for consistency during our testing. Using the AA utility, we can craft an Apple archive. We specify the target directory to be the images folder and output an archive named mypictures.aar. It's worth noting that AA utility intentionally archives everything under the specified directory. So in this case, we specify the target directory to be the images folder, and it will only archive the files and folders within that directory, excluding the images folder itself. So once we have our mypictures.ar file, we can host it on the internet, download it, extract it with archive utility, and we have the following directory structure. So when an archive is downloaded from the internet, as Jaron mentioned, it will hold the extended attribute, and Gatekeeper will check for this attribute to see if it's been downloaded from a remote source or if it should be allowed to execute. So as we see, archive utility will apply the quarantine attribute to all of the extracted items as expected. So now we can take this directory structure and using the same command, we can craft an archive. However, this time we will add an additional photo named for.png to the root of the images directory. Again, this will output an archive named mypictures.aar. Let's see what happens when we download this. So upon downloading and extracting the archive with archive utility, we have the following directory structure. Here we notice something very interesting with how the quarantine attribute gets applied. There's two important things to note. First, we see a new folder name called mypictures. Second, this newly created folder, mypictures, does not have a quarantine attribute applied to it. So archive utility has created this mypictures folder. We didn't originally put that in the archive. So how exactly did this folder get created? It's pretty interesting. So we'll look into the discovery of how this non-quarantine folder got created. So as we recall, we only noticed this behavior when we added the for.png photo. It turns out when extracting an archive containing 2 or more files or folders in its root directory, archive utility will create a new folder based on the specified archive name. In our case, the root directory of our archive contained a folder named photos and a file named for.png. When our mypictures.ar file was unpacked, archive utility created a new folder named mypictures containing our extracted files. And presumably, this feature exists to prevent many files being extracted to the current directory, making it inconvenient to move or download or move or delete. Instead, it places these files in a new folder. So there are a number of processes that are involved when extracting an archive. This includes archive utility, archive service, and AU helper service. We'll start by looking at the archive service process. Archive service process writes the extracted contents to a temporary directory located at the path prepended with the name nsird archive service. Within this temporary directory, it will hold our extracted archive files and folders. Here we can see our photos folder and our various images as expected. Archive service will also aim to apply the quarantine attribute to all of the extracted items located within this temporary directory. It does this by calling a function called propagate quarantine information as part of the BA decompressor class. This function is responsible for propagating quarantine attributes to all the extracted contents of the archive. It invokes a low-level function titled quarantine file applied to path and libquarantine.dilib, which applies the quarantine attributes to the unarchived files located in temporary directory prepended with the name nsird archive service. And it will ensure that the quarantine attribute is propagated to all of the extracted contents. What we notice is that the quarantine attributes were indeed being applied to all the extracted items within our archive, including the photos folder and our images. However, archive service failed to apply the quarantine attribute to the nsird archive services folder itself. We will look at why this is really important when the temporary folder is renamed. The AU helper service process invokes a function titled decompress move copy results to move the extracted contents from the temporary directory to the target destination. Therefore, the nsird archive services folder is renamed accordingly, moving it to the target destination. And as mentioned, that's typically the user's downloads folder. Let's take a closer look at some of the disassembly for this function to determine what's happening just before the extracted archive is moved to the final destination. First, the function retrieves the path to our extracted archive located in the temporary directory. The function then retrieves the path to our downloaded archive. The file name of our archive is extracted from the path. The file extension of the archive is removed. And the non-quarantine temporary folder holding our unarchived files is renamed to its destination folder. So as a result, the mypictures folder does not have a quarantine attribute applied to it. Looking back at our directory structure for our archive when extracted with archive utility, we see that everything below the renamed directory mypictures receives the quarantine attribute as expected. Simply placing an application within this folder will not result in any success, as it will hold a quarantine attribute. So, however, as we learned from the Safari Gatekeeper bypass that Jaron just covered, when it comes to application bundles, Gatekeeper only cares if the app directory itself has a quarantine attribute, and it disregards recursive files within the app directory. Therefore, by ensuring our non-quarantine folder is an application, we can craft an archive in a way allowing us to bypass Gatekeeper checks. Let's take a closer look at some of the requirements for exploiting this to bypass Gatekeeper. As mentioned, the folder name containing our unarchived files is controlled by the user because archive utility creates this folder based on the specified archive name. Therefore, we can name our archive something like test.app.aar so that when it is unarchived, it will have a folder named test.app. Within this app, there will be expected application bundle holding the executable. And again, there should be 2 or more files or folders in the root directory, in the root of the target directory being archived in order to trigger the auto renaming. And remember, we only need to archive the files and folders within the app, as this will hold the quarantine attribute, although we need to ensure the root of our application is not contained within the archive so that the quarantine attribute is not applied to it. So in our exploit, we have an application named toxic.app. We need to ensure that all the conditions for exploitation are satisfied in order to bypass Gatekeeper. So again, there should be 2 or more files or folders. Again, we have the contents. We'll add additional arbitrary file named folder2. And next, we want to archive the contents within our application. We do not want the toxic.app to have a quarantine attribute. So using the AA utility, this is already accomplished for us. And so it does not include the target folder in the archive. And finally, we can simply name our archive as toxic.app.aar so that when extracted, we have a non-quarantine folder named toxic.app. So let's break this down, what's going on in the background when the user downloads the weaponized archive. First, of course, the archive is hosted and downloaded from the internet. Then the user clicks on the downloaded archive, causing it to be opened by archive utility. One of the reasons we actually used an AAR file, because if we use the zip, Safari would likely try to auto-unzip it. And we wanted to make sure that this can bypass when downloaded from any browser, so we used the Apple archive. As mentioned before, archive utility relies on 2 different service processes in order for it to perform its unarchiving. These are archive service and AU helper service. Archive service is responsible for creating the temporary directory. Then he begins to unarchive everything into that temporary directory. Next, archive service goes through the recursive contents of the directory and applies the quarantine attribute to each folder and executable under it. And notice here it did not apply the quarantine attribute to the temporary directory itself. AU helper service then takes over responsibility of renaming the temporary directory. Remember, it does this by looking at the original name of the archive that was open and then removes the file extension. This is why we've chosen to put 2 file extensions on our archive. And the name here will be used, that's going to be used for the renaming is toxic.app. And finally, it renames, and we have our malicious application with no quarantine attribute attached to it. And as we learned from the previous CVE, this is the only thing Gatekeeper checks for. And that is ultimately how our application goes about bypassing Gatekeeper. So as we mentioned before, this is not specific to Apple archives. Using the same application structure for toxic.app, let's craft a zip archive in a similar way to bypass Gatekeeper checks. So again, we'll check to see there's 2 files or folders. We'll archive everything within this directory. And we'll do this by simply changing directories to go within the app and then run the following zip command to archive all the contents within our current directory. And again, we'll name our application or our archive text.app.zip. And this will allow us to bypass all of Gatekeeper's checks when downloaded and extracted with archive utility. So after reporting our findings to Apple, they quickly patched the issue by updating the propagate quarantine information function. And they added an additional call to quarantine file applied to path, so that the temporary directory prepended with the name NSRD archive services now contains a quarantine attribute before it is renamed. Let's explore how we can go about detecting this activity with using Apple's endpoint security. We can monitor for ES rename events, and then where the running process is AU helper service. Checking the original path has a last path component beginning with NSRD archive services. That will be an indication that there is an auto renaming of the temporary directory. Next, we can check that the destination path has a last path extension of an app, indicating an application is being extracted. We shouldn't ever really see an application being extracted where the original path has a last path component beginning with NSRD archive services. And as most developers would follow the correct and recommended directory structure, where you have a structure like test.app, contents, macOS, and then your binary itself. As an optional check, you can verify that the destination path is indeed an application that is unsigned or ad hoc signed. Looking at the raw ES data for a rename event, we see in our crafted exploit for the application named toxic.app, the original path has a last path component beginning with NSRD archive services, and our destination path has a last path extension of app, indicating an application is being extracted. When comparing this to a standard non-malicious application named safe.app, we can clearly see that the original path for this event has a last path component beginning with safe.app. And as it gets written to the destination, it gets written as safe.app as well. Since the application is located within the NSIRD archive services folder, it means it was contained within that extracted archive, so it will hold a quarantine attribute, which will not allow it to bypass Gatekeeper.
So today we covered kind of two different CVEs that are very similar in the way that the payload is created, but actually very different in how they're behaving behind the scenes. So 22616 was patched in 12.3, and 32910 was patched in macOS 12.5. When we find a new vulnerability, we always monitor for malware that might be abusing it. As far as we could see, there was nothing abusing this one, unlike the talk last year we kind of had where we saw Schlayer trying to bypass Gatekeeper. And if you want to slow either one of these down and kind of read them in blog form, you can do that on our Jamf Threat Labs website, where we've posted both, and we'll tweet those out later as well. So thank you so much for having us, and looking forward to some more talks.